last time I had talked about chemically gated channels, and I specifically gave you the instance of acetylcholine as a neurotransmitter, basically a chemical key that unlocks a channel in the membrane that can transiently lead to a transient change in the permeability of the membrane to a specific ion. Now, this is one of the last keys. So I guess, had I gotten to voltage yet? I had. This was the last thing I had said. So yeah, the voltage-gated channels is the last piece of the puzzle. All right. We had talked about the porins, the leak channels. We had talked about the not the FOF1 ATP synthase, the sodium potassium ATPase that was putting 3 sodium outside for every 2 potassium it puts inside, and helping to establish a chemical gradient, right? That is being modulated by the presence of the leak channels, and now that sets up this dynamic with the 2 ions that can lead to some dramatic changes in the membrane potential, because the potassium and the sodium have different equilibrium potentials, right? So potassium was at minus 90, resting potential is minus 70, potassium's equilibrium is at minus 90, and sodium's resting potential or equilibrium potential is at plus 66. Right? We're going to work off of those 2 things, but we need something to actually set this all in motion. And so we have the chemical gated channels, and then lastly these voltage gated channels. So a voltage gated channel responds can be either activated and closed, or open, or inactivated and closed, depending upon what the relative potential of the membrane is. And then lastly, is this concept of the mechanically gated channels. This is actually where I wanted to get to last time. And a mechanically gated channel is simply one that gets opened by deformation of the membrane. So you guys have, I'm sure, seen that, like airports in the novelty shops or whatever, those like sort of toys, those big balls that are kind of made of little sticks or whatever, and they open up real big, and then you can close them. These channels remind me of the same thing. And in fact, they have very similar architecture. So you see here on the bottom is this channel found in E. coli, a mechanically gated channel found in E. coli, that is normally closed down, but if you press on the membrane adjacent to that, it is able to draw itself open. All right, it's able to open up and allow the passage of whatever it is that is meant to pass through that channel. And this will be important as we talk about certain mechanisms in the body. Can you think of an example of where a mechanically gated channel might be useful? Yeah. In sensory receptors, yeah, in your hands. So touch would be an excellent example, yeah. We'll find out that they are in lots of different types of sensory receptors, not just touch in your hands, but all over the place. For example, your sense of balance, your sense of hearing, all of those are dependent upon mechanically gated channels, all right? So, and there'll be some other examples as well. All right, so I've given you the cast of characters. Now let's define a couple terms. Let's define a couple of the things that can happen. First of all, the concept of depolarization versus hyperpolarization. A depolarization is, so resting potential was at what? What did I say resting potential was? Negative 70, yeah. So a depolarization is going to be depolarizing the membrane, moving from -70 closer to 0. All right, so there's going to be less of an electrical potential across that membrane, depolarizing it, a decrease in the VTM. And conversely, the hyperpolarization is just the opposite. It's increasing. So going from the resting potential to the equilibrium potential of potassium, which was -90, would that be a depolarization or a hyperpolarization? So we're going from the resting potential at -70 to -90, which is the equilibrium potential of potassium. Would that be depolarizing the membrane? No, it's hyperpolarizing. Okay. Whereas moving from resting potential at -70 towards the +66 potential of sodium would be a depolarization event. Okay. So you can see how transiently changing the permeability of the membrane to either sodium or potassium could have different effects on the membrane potential. One could depolarize and the other would hyperpolarize the membrane. Okay, so this is now everything we need to be able to talk about the first membrane dynamic. Yes, Elizabeth?
Why is it not the other way?
You're thinking in absolute numeric terms, as if negative is an absence of something. In this case, the determination of negative is just, it's kind of an arbitrary distinction that we place on the charge characteristic of the membrane. There is a greater potential on a -90 membrane than there is on a -70. It just happens to be negative in character rather than positive, right? And so don't think of negative numbers and positive numbers when we're talking about potential in the same way that you would think about ordinal numbers, or not ordinal, but just like counting numbers or whatever. That's not the right word either. My number theory is failing me. Anyways, just regular numbers. 1, 2, 3, -1, 2, 3. It's just a designation of the charge characteristics of the potential that we're measuring. Does that make sense? Yeah. So, graded potential. A graded potential is inherently a local change in the transmembrane potential. Right? There's going to be some. So when you have a graded road, or going up a grade is just it's related to the word gradient. Right? There's just a change in some characteristic with space. Like you grade a road and you make it smooth between point A and point B, or you go up a grade, maybe it's a 5% grade. That means that your height is changing by 5% along a certain run of the road. All right, and a graded potential is the same way. So at the site of stimulation, you're going to have some kind of change in the membrane potential, and that's going to lessen as you get away from the site of stimulation to, at some point, you're just going to be at the regular resting potential at some distance in the membrane away from that site of stimulation. They don't spread. Whatever happened to the membrane does not spread across the membrane. It just very far from the site of the stimulation. So anything that is going to open some sort of gated channel is going to produce a graded potential. Anything that opens a gate is going to cause a graded potential. This can be a chemically gated channel, for example. Maybe we drop a little bit of chemical key, some acetylcholine onto the membrane. It's going to open up these channels, and we're going to cause perhaps a depolarization, perhaps a hyperpolarization in the membrane right on the site. So let's go through this step by step. Here we are at the resting state. So the membrane is closed and the potential is at minus 70. And then we release some sort of neurotransmitter onto the membrane, which binds to the chemically gated channel. So, we see this neuron and we apply some stimulus in the form of acetylcholine perhaps or some other chemical. Pardon me. Thank you. So these sodium channels open up, or whatever ion channels, these cationic channels open up, and I'm assuming it's sodium because they're showing the cation rushing in to the cell. That's what sodium would be. And it's as sodium does that, it's going to change, it's going to drive the transmembrane potential towards the equilibrium potential of sodium. And what did I say that was? It's a depolarization. What was the actual equilibrium potential of sodium? Plus 66. It was plus 66. So all the way through 0 and keep on going towards plus 66. All right. So we begin to get what's called a local current. Sodium flows in, and as it flows in, so for example, I'm sure you in general chemistry back in high school, you maybe remember, they'll have a big beaker of water and they'll put a drop of food coloring in it, and it's real dark where the water hits the beaker, and then it slowly spreads out. And the professor's giving their lecture, and after an hour, she asks you to look at the beaker, and it's like the whole beaker's now sort of a light blue or something like that, right? And so this is just diffusion, and there's this local current that happens. The sodium spreads out from the site of stimulation. So at the very spot where the stimulation occurred, we're continuing to depolarize. We're moving closer to 0 or towards plus 66, really. And it's spreading, this local current is depolarizing the membrane away from the site of the stimulation. But at some point, distant from that, the membrane is still at minus 70. All right, so that's a graded potential. So when it's a depolarization, this is sodium that's achieving this, and we're shifting the transmembrane potential towards 0. And when you think about it, it's simply, so here we are in this diagram, we're at minus 70 on the membrane. So this is a depiction of the membrane, but then I'm superimposing on it the potential of the membrane. At the site of the stimulus, you begin to have this depolarization. We're moving towards 0. So one of the things about this form of stimulation is, or this form of information encoding, because that's really what it is. It's encoding information in terms of the strength of the signal, or whatever the signal is, maybe the signal intensity or the rapidity, or however the information is being transferred, whatever information is being transferred. It's analog in nature. Do you guys know what I mean when I say analog? Analog versus what? What's digital? Analog versus digital, or something that's continuous versus something that's broken into quantized or discrete bits, right? And so a graded potential is analog in terms of the information it's encoding. It's a continuous change in the electrical field that's localized to that place in the cytosol on the membrane there. It's an analog form of information encoding. All right, and you may wonder why I make that distinction, but I'm going to talk about action potentials in a little bit, and action potentials are the opposite. That's digital encoding of information. All right, an action potential either happens or it doesn't happen. It doesn't have like a relative strength. In a graded potential, not all graded potentials are the same. You can have a graded potential. The size of the graded potential is dependent upon the strength of the stimulus that you applied. Okay? So you can have a range of strengths in the graded potential. That's an analog form of information encoding. Whereas with a action potential, all action potentials within a certain neuron are the same. And the information that's getting encoded is in how rapidly that neuron is firing an action potential, a subsequent one. Does that make sense? We'll get to that in a bit. But I just want you to see how the strength of the strength of the stimulus is going to dictate the degree of depolarization. On the other hand, potassium would give us opening potassium channels would shift us towards minus 90, and this would be a hyperpolarization. All right, this is going to increase the negativity of the resting potential. You can see here at the site of stimulus that it moves more negative, but as you move away from the point of stimulus, it's more like the resting potential of the membrane. All right. And when this happens, the positive ions, the potassium, are moving out of the cell. They're moving out of the cell because they're going down their chemical gradient. The electrical gradient is still telling them to come inside, but their chemical gradient is strong and is driving them outside of the membrane. Okay? Is there anything new here? Yeah, so this is all kind of, this is sort of a recap of everything I've said so far. The point being that with a graded potential, the effect decreases with distance from the site of the stimulus, and it's only able to spread passively through what are called local currents. The whatever ion it happens to be, presumably sodium, we've been talking about that a lot, that change is going to occur through local currents, both on the outside and the inside. To get maybe a little bit, just sort of hint at the deeper biophysics of this, when you look at this diagram here and you see the pathway of charge flow, as you have charge carriers moving, you're particularly in this sort of pattern like this, you're going to set up an electric field that's going to generate an EM field that is a pericellular EM field that does have implications in the deeper function of a neuron, for example. But that's just a hint. We're not gonna go for higher level classes to talk about that. All right. So on to the next bit. We just talked about a graded potential, a simple change in the transmembrane potential that's localized. Now we're going to talk about an action potential. So action potentials only happen in a special kind of membrane that has special constituents. The membrane type is called an excitable membrane. Is it an excitable membrane? An excitable membrane is one in which it's kind of like a set of dominoes. If anywhere in that chain of dominoes you begin to knock it over, the whole membrane is going to go through the same, is going to be excited, and is going to go through the same change in the transmembrane potential. All right? So it's all or nothing for an action potential. You're either going to initiate one or you won't. And if you initiate one, it's going to happen on all of the adjacent excitable membrane that's connected to this portion of the membrane. So the depolarization events tend to be large, and they happen very rapidly. And importantly, they're reversible. Once you trigger it, there are mechanisms in place to reset the membrane so that another one can happen again. All right, you can reset it. So when we initiate it, there's going to be this depolarization event that's going to then get propagated across the entire membrane. So specifically, this excitable membrane in a neuron, it starts at the axon hillock. Remember I talked about the anatomy of an axon a little bit? Starts at the axon hillock and is all of the axon up to the synaptic bouton through the telodendria, but none of the cell body or the dendrites. That is not what we would consider to be excitable membrane. You don't have action potentials there. You can only have graded potentials in the cell body, in the soma, and in the dendrites. All right. The thing about action potentials, however, is that it's able to link events that happen at the cell body and in the dendrites with synaptic activity at the telodendria. So whenever a cell is able, it's getting inputs and they're adding up to different electric fields in the cell body. When we reach a threshold at the axon hillock, that threshold is going to be, having met it, that's going to be what sets off the action potential. That's how the cell kind of processes information. It says, okay, I've gotten enough input to meet the criteria for signaling that I have as a neuron. So now I'm going to signal and send a rapid action potential down the cell body to the telodendria, to the synaptic bouton. And then we'll have a synapse, and the series continues. So if a cell is excitable, it has action potentials. If it is inexcitable, there's no potential for action potentials there. There's no possibility, potential is the wrong word, no possibility for action potentials there. So neurons and muscle cells are going to be ones that are excitable. And other cells, for example, epithelium or connective tissue cells, they're not. You can have graded potentials happen in other cells, right? But they're not. There are no action potentials that are possible in cells that do not have excitable membrane. All right, so let's go through these step at a time. First box, we're sitting there at the resting transmembrane potential, and we have two channels. You'll notice there is a sodium channel in purple and a potassium channel in orange. The sodium channel, both of them are closed. Presumably, there are other channels that are here that we're not seeing because they're not pertinent for what we're about to discuss, but there's going to be some leak channels. There's going to be some sodium-potassium ATPases. The exchange pump is going to be there, helping to maintain this minus 70 resting potential. So the sodium gate is open. I'm sorry, the sodium gate is closed, but active. It can open. And then, so we'll guess that these sodium channels and potassium channels are in the axon hillock, right next to the cell body. All right? And we begin to get this local current from perhaps a series or maybe just one really strong graded potential that is proximal or nearby the axon hillock. This local current begins to impinge upon this part of the membrane and is going to bring that membrane down. The potential, it's going to depolarize that membrane to a certain threshold, to a threshold value. At that membrane potential, the regulatory peptide loop on the sodium channel is going to swing away from the opening of the channel, and that's going to allow sodium to begin to rush in. All right? So the door swings wide, and now sodium ions are able to to rush in through the cell. And we have a rapid, powerful depolarization, or actually movement towards the equilibrium potential of sodium, which we talked about previously as being plus 66. All right? So we're going to head towards that. We're not actually going to get there. We're not going to get all the way there because some other things are going to happen first. So the inner membrane begins to change from negative to positive. And at a certain point, we're going to reach, and that point is plus 30. Two things happen at once here. First of all, at this potential, at plus 30, the inner leaflet, another peptide that's normally open on the sodium channel, is going to slam shut. It's going to swing closed and prevent any more sodium from traveling down its electrochemical gradient. At the same time, a similar peptide door on the potassium channel is going to do the opposite. It's going to swing open. And it's going to allow potassium to run down its electrochemical gradient. All right? And you can see, when the membrane is at minus 70, it's actually pretty close to minus 90, right? So the electrical component of the electrochemical gradient for potassium isn't especially strong at the resting membrane potential, right? But when you bring it down to when you bring it down to plus 30, when you've depolarized and flipped the polarity of the membrane, so you're now at plus 30, the chemical gradient for potassium has always been pointing strongly in this direction. But when we're here, the electrical gradient is also now really strongly trying to slam potassium out of the cell. All right? So when that channel opens up, potassium just starts flooding out of the cell. And as that happens, we reach minus 90. We go back to hyperpolarize the membrane towards minus 90, which is the equilibrium potential of potassium. And once we get there, a couple things happen. The sodium channel resets itself. Inner door is going to swing open and the outer door swings shut. And this potassium channel is going to begin to shut itself off. All right? So that's an action potential, and we're going to see what effect that has in just a minute. All right. So we got to talk about the refractory period, though. The refractory period is an important concept. It's this time interval during which the membrane is not going to be responsive to any amount of stimulus. All right? During a refractory period, you can send that axon hillock, that excitatory membrane, as much stimulus as you want, and it is not going to cause another action potential. The way that I think about this is, like, if you knock over, and this is probably not actually a very good analogy, but if you knock over a series of dominoes, the dominoes will fall down, and then you set them back up, and you can knock them down again, and on and on. But as the dominoes are falling, you don't really set the dominoes up again right while you're falling, right while they're falling. And you kind of can if it's a long series of dominoes. Maybe you could do it at the back end, which is like what is going to be this relative refractory period. But there's a certain point, like right near the wave of dominoes, where you're not really going to be able to go in there and set up dominoes to have another fall of dominoes right at the same time. So let's look at this. Along this axis is time. So be aware of that, because I'm going to show you another diagram in a minute where this is going to be space. It's going to be distance from the site of the initial stimulation, right? and it's going to look very similar. But for the moment, this is time in a single spot on the membrane, on excitable membrane. So here, and this is transmembrane potential. Here we are at the resting potential. And minus 60 is our threshold. That's our threshold. So we have some kind of graded potential that is going to cause, it has a local current that's going to like slightly depolarize the membrane right around the excitable membrane. And this transmembrane potential is going to reach the threshold. The sodium channel is going to whip open, and sodium is going to rush in. We're going to head towards plus 30, which is the equilibrium potential for sodium. But as we get up here, the voltage-gated sodium channel closes and the voltage-gated potassium channel opens, and sodium is not able to keep moving. In fact, it happens before this. It should actually be down here somewhere. But sodium begins to rush out of the cell and begins to repolarize the membrane. In fact, we head down towards minus 90. Okay. So during this period of time here, this is what's called the absolute refractory period. The cell cannot initiate another action potential at this point. Just can't. Whereas there's this right here. This is called the relative refractory period. Once you get close to reset, you can, with strong stimulus, potentially elicit another action potential. So it has to be larger than normal. Because even though the transmembrane potential is in the right range here, the cards aren't still completely set up yet, right? Because we have all this sodium that's outside the cell, all this potassium that's inside the cell. That sodium-potassium ATPase needs to like fix the chemical part of the gradient. Maybe the electrical part's more or less in range, but we got to get that chemical gradient reset a little bit. Despite that, if you have a strong enough, stimulus, you can still elicit another action potential. You could take off from here again for another action potential if you had a strong enough stimulus. Does that make sense? Yeah? No? Is everybody with me? No one? Okay. Because of this, we can get propagation. We can get propagation of this depolarization event. So propagation is simply going to move the action potential that is generated at one point, specifically the axon hillock in an axon, along, or the motor end plate in a muscle. It's going to move it along the entire length of the excitable membrane. In a neuron, that will be the axon, and in a muscle cell, it'll be the entire sarcolemma and T-tubule complex, but we'll talk about that next week. Okay, so we just went through the temporal profile, but that's a really crummy diagram. I'm sorry it's so lo-fi, but there's a spatial profile of it as well. All right, so at the site of stimulus, it's going to move. There's going to be local currents that are going to spread out across the membrane. And in fact, because of the architecture, the geometry of the structure of the neuron, the only place it's going to be able to flow is down the axon. All right. Because of the refractory period, because of this refractory period in pink, it's not going to be able to move backwards. It can't move backwards. It's only going to be moving in one direction across the surface of the membrane. That's important, right? Because if it was able to go backwards, it would just be constantly ping-ponging across that membrane and would never be able to reset itself. I think I have a better picture here. Yeah, here's a little bit better one. So here's the signal. we have an action potential happening here, depolarization. This membrane that just went through an action potential is in the refractory period, so the action potential is not able to move back, but nothing's happened to this membrane yet. So the local current that's being created here sets off an action potential here. But the area that just went through an action potential is now in refractory period, so it's not able to move backwards, and so on and so forth. So it just moves down the length of the axon. Does that make sense to people? Yeah. It's kind of beautiful, if you ask me. It's a pretty elegant thing. All right. So there's a couple different methods of propagating action potentials. And the most sort of simplistic and straightforward one is called continuous propagation. And this happens in axons that are unmyelinated. So maybe in high school biology or maybe in 163, 64. I don't know what they talk about in that class. I've never sat in on it. But you probably heard of myelin before. For those of you who haven't, myelin is an insulator, we'll talk about it in a moment, that gets wrapped around the axons of some neurons. But before we get to that, the first method, the most straightforward method of propagation of an action potential is just continuous propagation. So this is just continuously affecting the entire length of the axon as you move down from one bit to the next. So as we see here, there was a depolarization event at the axon hillock in segment 1. This sets up a local current which drives the adjacent membrane at 2 towards the threshold. That will start an action potential there, while segment 1 goes into the refractory period. Segment 2 begins to have sodium influx, and that's going to cause a local current which is going to send the next segment, segment 3, to threshold, which is also going to go through the same mechanism here. All right, so all of this is unidirectional, goes in one direction, and it's actually kind of slow. 1 meter per second is actually pretty slow. It's a pretty slow mechanism. All right, the second method is saltatory propagation. So continuous propagation in axons, there are a few axons in humans like that. There's a few examples of that in mammalians. In fact, chordates in general don't have a whole lot of examples of continuous propagation, but for example, squids and animals like that, they have neurons that do continuous propagation. In fact, they're used quite a bit in neuroanatomy labs, neurobiology labs, I guess, because due to the fact that it's continuous propagation, the cross-section of those axons is quite large. We'll see, I'll show you an equation for that in a little bit that'll help you understand why. Saltatory propagation is when we have myelinated axons that have myelin. So it insulates the axon, and it prevents continuous propagation, but it gives us something important. So the way myelination works is you're going to have this myelinated internode, and then separating them are these nodes. And what happens is you're going to have a depolarization event at one segment, and then there's going to be a local current, but it's because this myelin is here, essentially concentrating the electric field into the cytoplasm or the neuroplasm of the axon. It's going to allow for a much more rapid transfer of depolarization to the next internode. The myelin changes the I guess the permittivity, the electrical permittivity is the actual quantity, but that it's going to allow the electric field to jump from one internode to the next very rapidly, very rapidly. So the consequence is that, number one, it's much faster. Number two, the axons can be smaller. And number three, it uses less energy. Okay, because all this membrane along here, along the internode, is never depolarizing in the same way the rest of the excitable membrane is. So there's no sodium-potassium ATPase that's burning ATP to establish the electrochemical gradient through there. All right. So here are the steps. So we have depolarization at segment 1. Local current rapidly causes a depolarization to jump to segment 2. The exact physics of this is a little bit sophisticated. It's a little, to actually get into the gory details of the physics of it, it is a little bit beyond what we're going to do here. But you just basically need to understand that as we have a depolarization at one node, there's a rapid jump to the next node that causes a depolarization, and then again another rapid jump. So it can sort of leapfrog down the membrane, down the axon, much more rapidly than it can in continuous propagation. All right, so here's that fun bit of math that I promised you a moment ago. The movement of these ions is related to the cytoplasmic concentration of them, of course. The axonal diameter is going to affect the speed. So in general, we have the velocity is proportional to this thing here, right? It's inversely proportional to the capacitance of the membrane. All right, so that means that as membrane capacitance goes up, velocity goes down. And myelination is going to help reduce the membrane capacitance. How much electric field does that membrane have the capacity to hold? By keeping it myelinated, you're reducing the capacitance of that membrane and increasing the velocity. And then same with membrane resistance and the resistance of the axonal neuroplasm. The membrane resistance is another aspect that the myelination is changing. So as and then lastly is diameter. So as diameter goes up, velocity goes up as well. All right, so we're able to trade off axonal diameter for the membrane capacitance. Those continuous propagation axons in squid get past the fact that they are not myelinated by simply becoming bigger. They become much bigger, and that's what gets their speeds back up more or less in the same range as the ones that are myelinated. This is why they're used in the lab, because they're huge. You can see them with your eyes and stick a probe in them. They're pretty incredible cells. All right. You don't need to memorize that equation, though. I'm just using it to help you rationalize what's happening. Anything else I want to make there? Yeah, you have to quadruple the diameter to double the velocity, whereas myelin insulation is a great way to reduce that. Yeah, so that's the thing. This is the square root of the diameter. So the diameter doesn't scale linearly with velocity the way the membrane capacitance does. Myelination is a really great strategy for making an action potential quicker. All right, so here's the all or none principle. And And I don't know, when I talk about this to students, sometimes I see them glaze over. All or none, you should be able to understand that. So that's, if you tip over the dominoes, they're all going to fall, right? You've pushed hard enough to start the chain reaction, or you haven't. And it's all or none. But here are some implications to it. There is this binary, either an action potential is happening or it's not, a sort of on or off type information transfer that happens at a synapse. So you have an action potential that's going to result in some kind of a synaptic event at the end of the axon. And that either happened or it didn't. It either happened or it didn't. This means that the informational content of an action potential is frequency encoded. Frequency encoded. How rapidly are subsequent action potentials happening? Are the action potentials like this, or are they like this? Or is it some complex pattern? Whatever. It's frequency encoded. Whereas, and that's this. Whereas, and I'll explain this in a moment, but whereas graded potentials are amplitude encoded, the strength of the signal. So, when you have a radio frequency, when you turn on the radio, most of you guys in the car, you probably listen to satellite radio or a CD player or your iPod or something like that, whatever. But when I was a kid, it was AM, FM radio, and your cars probably still have those, right? The difference, yeah, come on. The difference between AM and FM, AM radio, amplitude modulated radio, is one in which you have a carrier frequency. You have some sort of carrier frequency, whatever the call frequency is of the radio station, and they're just going to modulate the intensity of that signal, which is why AM radio sounds so crazy when you listen to it. It has that unique sound because the signal is getting amplitude modulated. Sometimes the signal is larger and sometimes it's smaller. So you see there's this larger wave, which is actually the signal, the audio signal, that's getting superimposed upon this very regular signal of the carrier frequency. Whereas with frequency modulation, you're going to have some frequency, but the actual frequency is going to change back and forth around. It's going to change back and forth around the central carrier frequency. So this is a frequency modulation. And just trying to get you to understand amplitude modulation versus frequency modulation. If this radio thing is more than you can grok, that's okay. It's just the notion that a graded potential is analog in terms of the information that it's encoding, whereas an action potential is digital. It's how many. It's the frequency. It's kind of like quality versus quantity distinction, if that makes sense. Any questions on that? Obviously close to the witching hour here. All that I had, this was the last slide. This is just a table summarizing everything that I've just talked about. On one hand, it's the list of features of a graded potential, and on the other, it's the features of an action potential. I'm not going to keep you here to go through to recap it. It's all the same stuff I've been talking about the whole hour. You can look it over yourself. Have a great weekend. Any questions? Nope. All right.